My name is Yihui. I am now a professor at EPFL, but until very recently I was a postdoc at MIT, which is where most of this work was conducted. And today I'll be talking about quantum advantage. So I have a specific quantum advantage scheme, but let's first explain the meaning of quantum advantage, which is to perform a task on which quantum processors can perform this task in a way that convincingly beats classical processors. So the first such claims have already been made. We have the 2019 experiment of random circuit sampling by Google with its Sycamore chip. And then we have also some demonstrations of quantum advantage with light, which come from the USCC Zhejiang computer and Xanadu Borealis computer. And what I want to point out is that these quantum advantage experiments are digital setups. But today I want to explore a different kind of quantum advantage, which comes from a more analog setup. So this talk will be about analog quantum advantage from random Hamiltonian dynamics. So this is based on this paper. So I'm first going to talk about the random circuit sampling proposal, which is perhaps the best known quantum advantage proposal. And this proposal is that the task is to produce bit strings from the output of a given random circuit. And here, this circuit description is provided to whoever is supposed to be performing this task. So the way you generate this circuit is that you apply Haar random nearest neighbor gates on a 2D architecture. And quantumly, what you would do to do this is you just run the circuit and then measure in the computational basis. Now, classically, what you may try to do is to classically simulate this circuit to produce samples, but this should be intractable. And so I want to explain the meaning of classically intractable because a good part of this talk will be devoted to proving classical intractability for my proposal, which is that there should not exist an efficient classical algorithm. And here, efficient means that the algorithm runs in polynomial time, where the polynomial is in the number of qubits of the circuit. And here, this algorithm is given as input a description of the circuit that, if it were a quantum device, it would be running the circuit. And it is supposed to produce samples from any distribution D that closely approximates the true circuit output distribution in total variation distance. So the intuition here is that why should there not exist a classical algorithm that does this? Well, the idea is that if your circuit is composed of Haar random gates, then there will be a quick buildup of volume law type of entanglement and long-range light cones. And so there should not be too much structure that you might be able to exploit to do a classical simulation of this task. So today we're going to ask the question of whether we can get quantum advantage in a more analog way. So as mentioned just now, most of the existing quantum advantage proposals and demonstrations come from digitally programmed setups. And I at least am interested in an analog scheme, but I'm now going to give you 3 reasons why you should also be interested in an analog scheme. The first is a very pragmatic motivation, which is that many experimental platforms natively run Hamiltonians. And so if you want to compile circuits into Hamiltonian pulses, this incurs overhead, not only in terms of the computational time needed to compile it, but also it could be introducing some kind of approximation error. And if you didn't have to do this compilation, then maybe you could get rid of that overhead. The second is a more physics motivation, which is it's kind of just an interesting question if random geometrically local Hamiltonian dynamics are classically tractable. And I believe all of us have the intuition that they should not be, but I have given strong evidence for this today. So there's also a motivation that comes more from complexity theory, which is that in order to provide evidence for my quantum advantage proposal, we also developed tools for average case Hamiltonian complexity, where instead of studying Hamiltonian problems and identifying the hardness of a Hamiltonian problem by the worst case instance, we think more about the average member of that set of Hamiltonians. And this is kind of understudied in the complexity literature. So one of my hopes is that some of the tools that I developed here could be applied to average case Hamiltonian problems as well. And so here is the actual proposal. So the proposal is to run a random geometrically local Hamiltonian for constant time. Now, what is the meaning of a random Hamiltonian? Here is the ensemble. You fix an architecture on which you put your qubits, and then you let pk be the set of k local nearest neighbor Paulis on that architecture. And the way I define a random Hamiltonian for a fixed k is that I basically put just a Gaussian term in front of every Pauli, and the Gaussian term is normalized. I mean, like this entire Hamiltonian has a normalization at the front. And so for the rest of this talk, we will set k equals to 2, and we will assume that the architecture is a 2D lattice, but the methods also extend to other architectures. They're not too sensitive to the lattice structure. So we will argue that this task of random Hamiltonian sampling with k equals to 2 is classically hard. So you might be wondering, doesn't the hardness of Hamiltonian dynamics just follow from trotterizing the Hamiltonian? Well, if you consider the circuit arising from trotterizing e to the minus iht, you might hope that you are then able to use RCS-style arguments to establish classical intractability, but at least I have not been able to do so. And one of the obstacles that I ran into is that if you trotterize e to the minus iht, where h is drawn from this definition of a random Hamiltonian ensemble, if you consider the resulting ensemble of circuits, that actually doesn't give us circuits with Haar-random gates, which, and the RCS-style arguments are quite sensitive to this. But another reason is that our techniques could also be used for Hamiltonian problems that cannot be trotterized, such as for Gibbs sampling. Okay, so I'm going to go over the complexity theory part, and I'm going to try and condense it a lot. So if you want a full explanation of the details, I recommend you to look at Bill Pfefferman's tutorial at QIP 2023. It's very good. So I'm going to cover two main points. So the first thing is that to establish hardness of sampling, I actually argue about a different task, which is the task of estimating a fixed output probability. And I'm going to show that this is sharply hard. And I'm going to do the above with the help of a worst to average case reduction. So I will explain what a worst to average case reduction is. So I will first start by talking about the two computational tasks. So just to establish some notation, H is an n-qubit two-local Hamiltonian from the ensemble that I mentioned before, and T is an evolution time. So I'm going to refer to this distribution quite a lot, and this distribution is just the output distribution of measuring this Hamiltonian time evolution in the computational basis. Now, these two tasks that I will talk about are both relating to this distribution. The first task is to simply sample from this distribution. And any algorithm that samples from any distribution epsilon close to the target distribution, I'm going to call an epsilon sampler. And we would like to prove that an epsilon sampler is classically hard. But instead, I will reason about this alternative task, which is about evaluating probabilities. So this probability evaluation task also is related to this distribution, but it's about evaluating the probability that this distribution outputs the all-zero split string. And if I can do so to epsilon precision, then I'm going to call this an epsilon evaluator. So we will focus on the second task instead, and I would like to explain why this is okay, and the reason is because of this reduction, which is already well known in the complexity theoretic literature, which is called Stock-Myers reduction. This reduction says that if I had a sampler, I can then, if I had an epsilon sampler, I can then transform that into an epsilon prime evaluator using the sampler as an oracle. So so it's okay to focus on proving the hardness of evaluation because the hardness of evaluation actually implies the hardness of sampling via this reduction. So I'm going to put the definition of an epsilon evaluator at the top because that is what we are trying to rule out. So the goal is to show that epsilon equals to 2 to the minus n evaluation for a random Hamiltonian for t equals to 1 is sharp P hard. Now, sharp P is it's considered to be like a class of very extremely hard problems. So I'm not going to explain exactly how it relates to the other complexity classes, but you should think of it as being much harder than NP. And so it has been already established that it suffices to do this. So what we actually are able to prove is we go quite close to this goal by showing that if instead we choose epsilon to be 2 to the minus n log n, then that kind of epsilon equals 2 to the minus n log n evaluation for a random Hamiltonian for t equals to 1 is sharp P hard. So there's, again, a slight gap in precision, but to my knowledge, there doesn't exist any sampling proposal out there that has closed this gap fully. Of course, for random circuit sampling and boson sampling, we are quite close to closing this gap, and the gap is much smaller than it is here. But hopefully this can be improved. So again, this pink statement is what we prove. And so there is something that is already established, which is that 2 to the minus theta n evaluation for a worst case Hamiltonian for t equals to 1 is sharply hard. But this fact here pertains to a worst case Hamiltonian, whereas we want to show this for a random Hamiltonian. So in order to bridge the gap, we do a worst to average case reduction. Now, what is a worst to average case reduction? So let's imagine that we have the set of all Hamiltonians where every Hamiltonian defines a corresponding problem of evaluating its probability of outputting 0. So to say that a problem is sharply hard in the worst case is to identify a set of instances such that any algorithm that succeeds on solving, that succeeds basically on any of these instances must be solving a sharply hard problem. But what is an average case algorithm? Well, an average case algorithm is one that succeeds on just most Hamiltonians. And so a worst to average case reduction is simply a way of arguing that you can use an algorithm that succeeds on the blue set to solve problems in the worst case set. And this is a worst to average case reduction, as the name implies. And why do we want to do this? Because if we can make such a reduction, then we can conclude that this average case algorithm A must also be solving a sharply hard problem, which is actually what we wanted to show. So here's the proof sketch. So the first step is to approximate every output probability by a polynomial in G. So recall that G is the coefficients of the Hamiltonian. And if I consider the probability of this Hamiltonian H of G outputting 0, and I do a Taylor expansion of this, then that is well approximated by this Taylor expansion if you choose the degree of the polynomial to be high enough. And the degree of this polynomial needs to be scaling roughly as the operator norm of Hg times t plus log 1 over epsilon, where epsilon is the approximation error that you want. So also, note that we can represent every Hamiltonian by its coefficients, which is because G is basically the vector of coefficients of the Hamiltonian. So this is a point in n-dimensional space. So so let's now represent every Hamiltonian by this coefficient vector. And so if we are sampling Hamiltonians from the average case ensemble that I mentioned just now, where you put a Gaussian coefficient in front of every Pauli term, then if every such Hamiltonian is represented by a point in n-dimensional space, then they actually concentrate in a shell of radius square root m. And the reason for this is because of concentration properties of the m-dimensional Gaussian. So I'm drawing this sphere to represent an m-dimensional sphere, actually. And the spherical nature of this diagram is really because the distribution from which I'm sampling the Hamiltonians is spherically symmetric. And as mentioned, because of the concentration properties of the Gaussian, most of these points should be concentrated in the shell of radius square root m. And so, oh yes, I'm also going to put the worst case Hamiltonian, G worst, kind of at the North Pole. And because the reason this worst case Hamiltonian is not inside the shell is because it's a worst case Hamiltonian, so it doesn't have to be inside the shell of square root m. Okay, so the goal of the worst to average case reduction is to say that if I had an algorithm A that can estimate T of G, where T of G is our polynomial approximation of the true output probability, with high probability over these blue points, then I can use these blue points to estimate the red point. Where by estimating the red point, I really mean estimate the value of the polynomial at the red point, based on the value of the polynomial at the blue points. And so the way we do this is to find the best fit degree 2m polynomial, and then do some kind of polynomial interpolation procedure. So this is, I think, a very natural idea, because you're dealing with polynomials. So what do we know how to do? We know how to do polynomial interpolation. Okay, so the proof sketch is really that this is actually a problem of multivariate polynomial interpolation, because we have to do polynomial interpolation over polynomials that have a support that is basically n-dimensional space. And so what we actually do is that we have to perform, okay, so there is a slight problem with this proposal, which is that you actually have to perform multivariate interpolation with error correction, because the blue points are actually going to be fed through this algorithm A, which then makes some kind of error in evaluating the value of the output probability. And because the algorithm A is allowed to make some kind of error, you actually have to do some kind of robust version of polynomial interpolation that is robust to the error that the algorithm can make. And this is very complicated. We know how to do univariate polynomial interpolation with error correction, but we don't really know how to extend this to multivariate polynomial interpolation. So as a workaround, what we can do is you can compose this multivariate polynomial interpolation out of sequential rounds of univariate polynomial interpolations. Yeah, I think it's quite difficult to explain the details, so I will just leave it at that. So I wanted to conclude basically by kind of going back to a talk that I think was quite influential, which was a talk by Scott Aronson at Simons Institute in 2023, and he also gave this talk in other places, which is that what we really are lacking now is a quantum advantage proposal with three properties: that it is efficiently verifiable, it's NISCable, which means it can be run on near-term quantum computers, and it solidly beats classical. So we know of proposals that fulfill any two of these three properties. And today, we also talked about a proposal that fulfills two of these three properties, namely random Hamiltonian sampling. Like random circuit sampling, it's very difficult to verify this efficiently. However, we don't know how to come up with a proposal that fulfills all three properties. But this was kind of the state of the art in 2023. And in 2024, John Preskill and Jens Eisert noticed that the state of the art in experiments is actually improving very fast, and they coined a new term called FASQ, which stands for fault-tolerant application scale devices. And the idea is that whereas NISC devices are unable to do fault tolerance, the devices that we are able to create now in the lab have some measure of fault tolerance built into them. And so it's a question of whether we can now use our new experimental capabilities to come up with quantum advantage proposals that hit this sweet spot. And in 2025, I think the message I really want to bring across is that, in addition to thinking of like devices that are digital and primarily intended to implement circuits, why not we extend our imagination to analog devices, or basically devices that are closer to what experiments can already do in lab. And if you were here on Wednesday, I actually talked a little bit about this paradigm of pseudo-entanglement, pseudo-random quantum states. And I think there was some skepticism about the implications of these pseudo-resources for condensed matter, because the main takeaway from these pseudo-resources is that it's impossible to detect a variety of effects that you might think are efficiently detectable. Now, if you think that there are physical effects that are efficiently detectable, I would like to suggest that you make a quantum advantage proposal out of it, because then you would be able to hit at least one of these circles, which is efficient verifiability. And with the advances in analog experiments, we can also be hopeful that you will also be able to hit the yellow blob. And as for the blue blob, that will require some work, but that is something that can be done. So with that, I conclude my talk.
Yeah, thanks a lot. We have plenty of time for questions.
Hi, thank you for a great talk. This slide is impressive because as we move away from NISC to FASC and FASC, it seems like it's moving away from efficient verifiability and being classified, going to the opposite direction. Okay, that's a joke. I have an actual question. So not question, like a discussion point. Like I very much agree with exactly what you said. Why not make a quantum advantage protocol out of it? But I thought about the following. Say, what is what we need? Okay, in physics, we know, okay, giving me Hamiltonian, I want to understand the material properties of which near ground state, for example, right? So I talked about it with, computer scientists, and then they're saying, oh, that's a trivial problem because there's no input argument. So usually computation, you have an input and output, and there's a meaningful computations. But I want to solve only one Hamiltonian. For example, like I give you like Fermi-Hubbard model on like, I say, like triangular lattice. I can write down Hamiltonian. There's no variable, just this particular Hamiltonian. I want to know the ground state wave function, whether it belongs to the which phase. So that's the problem. But this problem is kind of, to some computer scientists, trivial because there's nothing to try. The answer is yes or no. Once you figure it out, there's no computational task to do. So I find some like big discrepancy between what we physicists think like important problem, but what the computer scientist defines as a like formal definition of problem. So I want to hear about like what would be the way forward to like converge at some point.
Are you not able to solve like the Fermi-Hubbard model at small instances?
So it's like, yeah, exactly. So you have a one Hamiltonian, and to computer scientists, okay, finding the ground state of one Hamiltonian is like trivial, but I don't know what that means. Of course, I know what that means, but come on, that's not. So I was struggling, how we formulate physically important problem as a computer science problem, because it seems like nature is actually quite different. Like in some, I don't know why it's different. So you could say that, okay, so they intentionally introduce parameter, okay, the Fermi-Hubbard model, but as a function of chemical potentials, right?
So I think maybe we can't, people online can't hear.
Okay, so like maybe Immanuel Bloch said, like it's not solving one Hamiltonian. We could parameterize a Hamiltonian or parameterize like, temperatures or like chemical potentials to make it as a proper computer science problem. So that, that I take it. However, that's also problematic because if you have only one parameter, say chemical potentials, it's a one parameter family, and that is still very easy or trivial to solve in some sense. So in some sense, fundamentally, what we mean by hardness, it seems to originate from a different mechanisms, and I don't know how to pinpoint that. So that's my question / complaint.
So what's your intuition for why the Fermi-Hubbard model is hard?
Are there more questions?
Yeah, so yeah, it's done. It's not a proper question. So I wanted to hear if you have any thoughts.
It's interesting. I already see the description about how physics and the computer science think about the Hubbard model. Yeah. Anyway, sorry. Yeah. Thank you for this talk. For me, it's quite interesting that you put analog platforms together with the fault-tolerant applications. Because in my understanding, in the analog context, it's even harder to deal with any, experimental imperfections, which is equivalent to noise or errors, because you even do not have a really good model to describe how the error happens. So could you comment on that? Because particularly for all these sampling tasks, my understanding is like all this noise matters a lot regarding whether or not it's a hard problem or not. So in the analog setting, you also have uncertainties about your Hamiltonians, parameters, things like that. Mm-hmm. So how you view this?
Yeah, I think that's a great question. So like, this was just kind of like a proof of principle. And I haven't considered noise at all, but you are absolutely correct that the next thing to do is to consider how noise would affect this proposal.
I see. So now you assume you have perfect knowledge.
Yeah, everything here is assumed to be perfect. But there are some papers by Toby Cubitt that suggest that analog platforms are kind of like naturally noise robust. I never understood this claim, but maybe you can.
I think there's an answer to that. There's actually this nice work from Ignacio and Raul Trevedi on analogs, on quantum advantage for analog quantum simulation. I really like your talk. Really. But just in there, what they say, what it actually means is the scaling. If, for example, we in the experiment improve our calibration factors by a factor of 2, how much harder does it get for the classical experiment to simulate that? And that is, for example, for those problems we're talking about exponentially, becomes exponentially harder. So it's not about a given point in time. We can maybe for our certain precision or system sizes we can reach, maybe you can do it classically. But it's about if I increase my imprecision of my parameters by a certain factor, how much harder does it get to simulate classically on a classical computer? So that's what Ignacio and Raul have been working out, and I think that was at least an important contribution in the direction. But I also find it very interesting that you put the analog quantum devices beyond NISQ devices. That's actually very interesting. I never saw that. Thank you very much.
I think it was more of like
adding
using
that to the discussion.
I think it's more like the first quantum advantage proposals we were able to think of kind of came from gate-based devices, but I think people haven't really thought so much about using analog effects to do quantum advantage.
I mean, for us, it was more always an intuitive feeling, right, as physicists, but I couldn't put it like mathematically or computer science or really a rigorous proof to it. So I think it's very, very nice that you can do that now.
I mean, following that, I think there is a paper from USTC using this analog setting to prove some complex sampling task. I don't know whether you have seen that, but yeah.
Okay, I'll have a look at this.
Yes, thanks for the great talk. I think I will just ask Sunwon's question in a different way. So suppose you have like system with translation symmetry, but in principle, one can still vary the system size, right? Just because you can simulate like a 10 particle Fermi-Hubbard doesn't mean you can do it for 100 particles. So like, I guess maybe just a clarifying question, like, is there any statement about like what happens if you impose these additional symmetries, or what if you consider like physically relevant systems, but they can still have variable size? Like, does this result say anything about that, or is this randomness like is intrinsically important for the algorithm? And what happens if you interpolate between the two regimes?
Oh yeah, that's an interesting question. So I think we can rephrase the question as if the distribution or if the weights on the Paulis are correlated, does my does my proof still hold? Yeah, this is something that is a little bit non-trivial. I haven't spent too much time thinking about it yet. Yeah. Okay,
just for the record, like, so there isn't a classical efficient algorithm for Fermi-Hubbard model, right? Like, just to make sure. Like that,
yeah,
that is efficient for total variation distance, like whatever that.
Sure.
Yeah, thank you for the very interesting talk. So I have a question about how this connects to, there is an algorithm for efficient sampling of shallow 2D circuits by Aramharo and others from a few years ago. That's for circuits, obviously, so that doesn't naively apply to continuous time evolution, but I would expect there is a way of tractorizing your problem where you can sort of still apply similar algorithm. So I would say there is a finite critical depth below which sampling is easy, and then sort of above that constant it becomes hard. So in your theorem, what are the, what is the precise statement about the depth? You're saying it's constant time, but is there such a threshold that appears, or? Let's say for a fixed
no, I only
normalization
time
of the Hamiltonian, right?
I only consider constant time.
Of course, constant, but like large enough constant, like are there any numbers that appear in the?
At some point, okay, so the way you can think about longer times is you can think about changing the distribution from which you sample the Gaussian coefficients, right? You change like the normalization of the distribution. And at some point, if the distribution is like too peaked, which corresponds to making the time longer, the polynomial interpolation should get harder. Because
the polynomial extrapolation becomes harder.
Yeah, because like you have to interpolate to the worst case point, which doesn't change. But your average case points are now being sampled from a Gaussian, which has very small like variance. And so like you have a longer distance to interpolate, so it should probably get harder.
But so maybe I'm confused, but it sounds like you're saying that at longer times, this worst to average case reduction becomes harder, and so your results become weaker at late times, but I would expect on the contrary, like short times this should be easy, and then at late times it should become harder to sample.
So for, yeah, maybe there is like, maybe this thing breaks down at short times. I'm not sure.
Okay, well, thank you.
Yeah, I think another question.
Proper technical question. So you are not able to show 2 to the minus n, but 2 to the minus n log n.
Yeah.
How does it propagate to the final like hardness of the sampling task? So is log n really like important or not so much?
Oh, I mean, like, we cannot, so like, you have to be able to show 2 to the minus n in order to really make a statement. Like, yeah, and like, I have only been able to show 2 to the minus n log n. So like, it doesn't connect up fully. So, yeah. But this is kind of also the same for RCS.
Because my thought was you should count the number of quantum degrees of freedom differently in the Hamiltonian system because there's energy conservation. And because of locality, there's a concentration of energy. So you might want to, in order to do the fair gain, you should not talk about scaling in terms of n, but square root of n, something like that.
Okay.
So we can talk maybe more, yeah.
Yeah, thanks for the very nice talk. I'm not sure I got where it was important for this system to be in higher dimensions, like dimensions higher than 2. I suppose your result.
It doesn't have to be.
But I guess for 1D it should fail, right? Or for 1D in constant time. Where does
Oh, for 1D, so you need to have your ensemble needs to include the worst case instance. For 1D, like there is no worst case instance.
I see. So that's why it requires higher than 2 dimensions.
Because it's a worst average case reduction.
Mm-hmm. Thank you.
Yeah, please.
Thank you for the nice talk. I have a question relating to the previous question. So what is the worst case Hamiltonian in 2D?
Oh, yeah. So I used this proposal of Dominic and Juani and other people. So they showed that if you run Ising Hamiltonian on a random product state, then that includes like IQP hard computations. So I managed to make this into a statement about like fixing the state.
Conjecture or
sorry?
Is it conjecture or proven?
So the fact that this kind of Hamiltonian time dynamics can encode IQP hard computations is already proven. So the conjecture here is like how hard is IQP?
Okay. I see. Thank you.
Please.
Yeah, I think my question is following up to Sonwon's. Do things change if the Hamiltonian is time dependent? And because that would be in some sense closer to a digital circuit than completely time independent. I mean, I saw it's on your slides, you seem to assume time independent, but how much does that matter?
Yeah, my proof is only for time independent Hamiltonians.
Okay, there's more questions.
Thanks for the nice talk. I just also have a question about the 1D. I'm actually confused because say you have 1D, if let's suppose the time is order 1, but it's very short, right? If you start with some random product states, you have an MPS representation of that, short time evolution with geometrical locality, the final state will have very low entanglement, which means I can represent it exactly as MPS with finite bond dimension. And I can always sample it MPS efficiently. So what is contradicting here? What's the worst case?
My proof doesn't work for 1D because the proof is based on a worst average case reduction. And in 1D, there's no worst case because as you said, in 1D, it's...
Oh, that's what you mean. Okay, so you do have to go to 2D and higher to have to contain worst case. That's what it's, okay, then I misunderstood. Thanks, yeah.
Maybe I had one more question. Like, about the properties of your output distribution, do you have anti-concentration also on this distribution?
Oh yeah, I don't know how to prove anti-concentration.
Okay, I see.
I think that there are very few tools to prove anti-concentration for like Hamiltonian time evolutions.
Okay. And like for example, the random sampling experiment, random circuit sampling experiment, you had like, as long as you could simulate, you had like methods like the XAB benchmarking for checking the fidelity. As long as you could simulate it on a classical computer, do these methods, would they work for these kind of distributions that you have?
Sorry, you're talking about XAB benchmarking, so are you talking about like verification?
Yes.
Yeah, I think so.
Okay.
Yeah, because this is just like producing samples. You can just verify with XAB.
Are there more questions? Yes.
I'm not sure what task you're describing.
Like I start from an initial state and perform some measurement to induce a final state. On the final state, I can perform this sampling as well. And then here, the parameters are the measurement outcome
Yeah, I don't think the techniques here would really apply to that setting, because here your measurements are kind of like adaptive, right? Yeah, so I don't think we would be able to say anything about that.
More questions? And I think we can thank the speaker again.